This is video number 1 in our series Topic in Tensor Analysis. In this video, we want to introduce the concept of contravariant and covariant tensors. Probably we're going to restrict our discussion in this video primarily to contravariant tensors and just try to introduce the concept, hopefully in a way that's meaningful, so that we can kind of build a conceptual framework that we can build upon in the future videos. And a reminder that the playlist for the videos is featured at the website digital-university.org. Okay, to get us started, let's say that we have two types of curvilinear coordinate systems. And notice how we have the coordinate axis labeled here. This is like the x-coordinate frame. This is x1, x2, x3, x4, and the numbers that we're using to designate the coordinate axis with, notice here we write them as superscripts. And that's going to be the convention in our videos. And then, say there's a different curvilinear coordinate frame, the y-coordinate frame, with y1, y2, y3, y4, and so forth. And we assume that we know how to transform from one coordinate system to another coordinate system, so that if we know what the x components of something are, then we know the rule for determining what the y component is. And likewise, if we're in the y frame and we know a particular component in the y frame, we know what the function is to give us the particular component in the x-coordinate frame. For example, let's say that we have our spherical coordinates here. Let's say that that is our curvilinear system that we're interested in. Here then are the Cartesian coordinates, and notice how we have the axis labeled x1, x2, x3. We have a point here, and for the spherical coordinates, its axes are the magnitude of the position vector, and then theta and phi. So these are the curvilinear coordinates here, and then the other coordinate axis that we have is the Cartesian coordinate system. And we know how to transform from one to another. That's with these equations. The x1 component in the Cartesian system is equal to this. Same thing for the x2, or similar expression for x2, another one for x3. So if we know what the spherical coordinates are, if we know what theta and phi and the magnitude of the position vector are, then we can determine what the Cartesian coordinates are. Likewise, if we know what the Cartesian coordinates are, if we know these, then we can determine what the spherical coordinates are. So we can go from one coordinate system to another coordinate system because we know what these transformation equations are. And we're assuming now that for our generalized curvilinear system, where here we have an x-coordinate frame and a y-coordinate frame, likewise we know how to transform back and forth from one coordinate frame to another one. And let's pretend we only have 4 axes shown here, but let's pretend that we had d number of them. So each vector would have d number of components, either in the y-coordinate frame or in the x-coordinate frame. And what we want to do is, let's just consider a simple displacement vector. We'll just draw, say, coordinate axes x1 and x2 like this. X2 looks something like this, and x1 was something like this. And let's just say that we have a small displacement vector here. Well, we know our displacement vector is going to have a displacement component along the x1 axis. Like this. Likewise, it will have a displacement component along the x2 axis, and for all the rest of them too. Until we get to the last one, like this. Well, the same displacement vector can also occur in the y-coordinate frame, and we're going to have just a similar composition then. It will have a differential displacement along dy1, dy2, and so forth. Incidentally, for our videos here, the way that we label these axes here with superscripts instead of subscripts, that's going to hold for all the videos that we're going to be engaged in. And that's pretty much the convention in all the textbooks that you see. Okay, now, let's say that we had a displacement vector in the x-coordinate frame, and we wanted to know, well, how could we express that in the y-coordinate frame, assuming that we know how to transform from the x-coordinate to the y-coordinate. How could we do that? So for example, what would dy1 be? If we know what all these are in the x-coordinate frame, and we know how to transform from the x-coordinate to the y-coordinate, how can we determine what this would be? And really, that's just simple calculus. dy1 would just be the partial of the y1 axis with respect to x1 times dx1 plus the partial of the y1 axis with respect to x2 dx2 plus the partial of the y1 axis with respect to the x3 axis dx3 and so forth. And we can find these partial derivatives because we know the transformation equations. Likewise, for dy2, it's going to be a very similar expression, except for having 1, we're going to have dy2. And we're taking derivatives with respect to x1, x2, x3, and so forth. And here, as in the x-coordinate system where the vector has d number of components, it's going to have d number of components in the y-coordinate system. So go all the way down to dyd, and again, it's going to be a similar expression to what we have written above here. So all of these equations right here can be summarized in this consolidated equation, where here we say a particular component of dy, which is called dyn, that's equal to the partial of yn with respect to xm dxm. These always stay the same, so this is xm dxm. And we can write it now, when we write in this consolidated form, we're assuming the Einstein summation convention. That is, when you have a repeated index like this, where it occurs upstairs and then again downstairs, well, it's still upstairs, it's a superscript here, but it's in the denominator. And when you have a repeating index like that, that means automatically that you're summing over that index. So m goes from 1 to 2 to 3, and so forth, all the way on out to the value d. So for example, if n equals 1, we'd have dy1 equals the partial of y1, and then m varies from m equals 1 to m equals 2 to m equals 3, and so forth. So this is just a condensed way of writing all of these equations. And in fact, we can think of it as this is a column vector, this is a column vector, and then these partial derivatives form a d by d matrix. Here would be one column of it, another column, where we go down d number of rows and we go across for d number of columns. So this would be a d by d matrix. We don't have to get into that right now. What we want to consider is this. This tells us then how a displacement vector transforms from one frame, the x-coordinate system, over into the y-coordinate system. And to be clear about this here then, these are the components of dy. And there are, as we said before, d number of those components. Now, so this can be sort of the components of the dy displacement vector, and here are the components of the dx displacement vector. And here then is how we can transform from the dx displacement vector into the dy displacement vector. Now, what we want to do is consider that same concept, only generalize with it. Here's the equation that we have. In fact, we can get rid of some of this material here. Or actually, we can just move the board up, I guess. Okay, so we have this equation that dyn equals the partial of yn with respect to xm dxm. Now, let's generalize this. Let's suppose we have this kind of a situation. Same types of derivatives, only here I'm going to write this in. Okay, this means that we have a vector that's expressed in the x-coordinate system, and this is a particular component of that vector. If I can find the corresponding component of that vector in the y-frame by taking these types of derivatives here, just like we did for the displacement vector, then we say that this vector is a contravariant vector. Its components transform into the y-frame completely analogous as to how a displacement vector transforms from the x-frame into the y-frame. And when you can transform that analogously to how the displacement vector transforms, then that's called a contravariant vector. And those are depicted then by having their components written as superscripts. So in general terms, that's what we mean when we talk about a contravariant vector, or a vector that has contravariant components. Now, let's just say that we want to generalize this from a vector concept into a tensor concept. So what we had written before was this. dyn is equal to the partial derivative Now, incidentally, when you have these repeated indexes, which automatically means that you're summing over them from m equals 1 to m equals 2 and so forth, sometimes they will call those dummy indexes, because we could replace this, say, with it gives the same expression. S goes from S equals 1 to S equals 2 to S equals 3 and so forth. So sometimes those repeated indexes, they will call them dummy indexes for that reason. Okay, we had then the transformation properties of our displacement vector or its components, and then we generalized on that concept like this. This is y. We don't want this anymore. We're generalizing now. We're here then, if we have a vector in the x frame and its components transform into the y frame by taking these partial derivatives, just like you do for the displacement vector, then that's a contravariant vector. Now suppose then that we have two contravariant vectors, say a in the y frame, and we have an nth component. Now then that means that would transform something like this. We're here. Here's the vector A in the x-coordinate system. We have a particular component of it, the rth component. And again, by taking these partial derivatives, that gives us then the component of the vector in the y-coordinate system. And here then we have over the repeating index r. Okay, and let's say we have another contravariant vector in the y frame. And how does that transform? It's going to be entirely analogous, of course. We're going to have something like this. And then for our repeating index, let's use S, like this. So here then, the vector now in the x-coordinate system, a particular component of it, transforms into a particular component of the vector in the y-coordinate system, again, by taking these same types of partial derivatives. Okay, now what happens if we multiply these two together? Now what we have here then, this has a total of d number of components, and this has a total number of d number of components. So you could take one particular component here and multiply it by all of the d number of components that this vector has. Then take another component here and multiply it by all these d number of components. And keep doing it for the d number of components that this has. So when we do that, we're going to have d squared number of components. And we can represent that just simply as mn. This just means that we're multiplying components together, and instead of having these two here, we'll consolidate that into a single symbol, this. But this would equal what? Well, it would equal this times this. So we'd have and then here, then we have this times this. Like this. Or these two we consolidate into this type of symbol. This just means that we're multiplying all the components by each other. So we can say this is equal to And then for these, we consolidate that into this type of symbol. Like this. And hopefully we've kept things in focus here. Okay. So here then, this would be called a tensor of second rank because we have one set of components, we have another set of components. There's d number of components in each set. We'll multiply them together. Same thing here. But we're asking ourselves, then, if we have such an object in the x frame of reference, how does that transform into objects into the y coordinate frame? And indeed, if it does according to this setup right here, then this is said to be a tensor that has contravariant components. And here we can see that it's easy to remember. Here we're in the y coordinate frame, and here we have superscripts mn. Here we're in the y coordinate frame, we have the superscripts mn. Now here, these have to be the repeating indexes, which means that they have to appear in a denominator here and here. So this is sort of like the general pattern then of a contravariant transformation. And again, in this video, we're not going to give try to explain the deeper meaning of it. Right now we just want to kind of get the general concept and just sort of get used as to the machinery where we can transform one contravariant tensor into another contravariant tensor with this type of setup here. And again, the idea of taking partial derivatives like this all stems from the way that a displacement vector transforms from one frame, the x frame, to the y frame. Entirely analogous. And that, in a nutshell, then, is the idea behind what a contravariant tensor is. Okay, come back, join us in the next video. We're going to sort of introduce the general concept of covariant tensors. Then after that, we'll try to get into the deeper significance of those two terms.